Hi, my name is Manish Gupta, and in this video, I'm going to talk about Meta's DinoV3 model. So let's get started and sort of understand what is new in DinoV3, what is the architecture, what is the pre-training method, how does it perform, and so on. Okay. So there have been several vision foundation models, and DinoV3 is a vision foundation model. The story started from CNNs. There has been 2012 onward, there has been LXNet, then VGGNet, Inception, ResNet, DenseNet, JFT, all of those CNN-based models. And then somewhere in 2019, we started off using transformers for vision foundation models, starting from CLIP, which used the contrastive loss, and SIGLIP, which sort of used the sigmoid loss. Right? Then people added more data and did more rigorous training, and that led to SIGLIP2 and perception encoder. Now, in that line of work, DinoV3 is a new vision foundation model. It follows the DinoV2 kind of line of work. It is a universal vision encoder with 7 billion size. So there's a 7 billion sized model, the largest DinoV3 model. And there are smaller models as well, which have been distilled to the Vision Transformer family, which is VIT, and ConNext family of models, which are sort of, on the transition of CNNs and transformers in that sense, right? So as you can see from this table, the VIT 7 billion is the largest in size, and then there are 4 ConNext models, tiny, small, base, and large, and there are 5 Vision Transformer models of different sizes that you see here, right? So that's that. Now, the nice part about DinoV3 is that while training it, they have scaled both the supervision, self-supervision data and also the model size. So as you can see, this is like 7 billion sized model, and you can also see different scales of model sizes. But they've also scaled the self-supervision data. In fact, the pre-training data comprises of 3 different parts, which have 2 of these parts have been obtained from a large web collection of images, which is like 17 billion in size. So on this 17 billion web image dataset, they performed hierarchical k-means, at 5 different levels in the hierarchy, so as to get 200 million clusters, 8 million clusters, 800K clusters, 100K, and 25K clusters. Now, from these, they obtained 2 parts of the dataset. The dataset basically pre-training data is in 3 parts. So the first 2 parts are actually obtained from this hierarchy of 17 billion images. So the part 1 basically comprises of 1.6 billion images. That's basically just a balanced coverage of all visual concepts across the various clusters in this hierarchy. Part 2 essentially is retrieval based. So you retrieve images that are similar to those from selected seed data sets, their captions and so on, right? And then part 3 basically leverages existing available large public data sets like ImageNet 1000, ImageNet 22,000, Mapillary, street level sequences, and so on. Okay, so that's how they have scaled the self-supervision data to train a very rigorous model. So the VIT 7 billion model actually has about 7 billion parameters, as one can imagine. It also has like 40 layers. So that's the 40 layer model with a patch size of 16. It uses rotary position embeddings, but with a little twist. So we'll talk about the twist on the next slide. It also uses register tokens so as to ensure that they are not much artifacts, the attention heat maps and so on. Otherwise, yes, there are other things like 32 attention heads and SIGLU activations and so on. Okay. So the new thing that DinoV3 has added on top of DinoV2 model is this gram anchoring technique. And we'll talk in detail about what is gram anchoring. But in short, they've added this technique so as to avoid degradation of dense feature maps during long training. So when you do continuous training, dense feature maps can get degraded. And to avoid that, they basically brought in this gram anchoring. They've also designed a few post-hoc techniques to enhance the model's quality, including improving the resolution of images with which it can deal, coming up with distilled models of various sizes, and also alignment with text in a clip kind of manner. Right. So overall, these DinoV3 models, basically the largest one, establishes state-of-the-art on object detection and image segmentation benchmarks. Thus, if you think about it, DinoV3 is a really good vision foundational model, a generic encoder that can be used in various complex computer vision systems. Right. So let's basically delve deeper and understand how is DinoV3 model trained. So DinoV3 basically has been trained primarily using the DinoV2 recipe, right? So, and I'll basically quickly recap in this video how DinoV2 has been trained, and rather what is the recipe and how is DinoV3 slightly different from that recipe and so on. Okay. So in DinoV3, the learning objectives are both of the learning objectives that were there in DinoV2 have been taken here. So the image level objective and patch level latent reconstruction objective. So just to basically understand these two objectives, let me basically just talk about this picture. Right. So in fact, the overall learning objectives in DinoV3 can be understood from this last equation that you see here. It's a dino loss plus the I-bot loss that I'll talk about, plus 0.1 times the divergence scolio loss. Okay. And the scolio loss I'm going to talk about as well. So each of these three components we'll understand one by one after we look at this picture. Okay. So at train time, essentially, when you get an image, you basically get two different views of the image. So, and these two different views are just obtained in a data augmentation kind of manner. So you could basically blur the image or, do some rotation and so on and get two different views of the image, right? U and V. Now, for both of them, you essentially, send it to a student model or a teacher model. Both of these student and teacher models, both of them are of the same size in that senses. Okay. And to the teacher model, you basically do not mask any of these tokens in the image, but for the student model, you mask a few tokens in the image. And the idea behind this iBot-based patch level latent reconstruction loss is masked image modeling. And in masked image modeling, you're actually trying to do this latent reconstruction of the patches. You mask the patches, and then you expect the model to unmask those patches, right? So the idea is that you basically pass these masked things through a student model, masked representations of both U and V through the student model. You pass the unmasked ones through the teacher model. And then on the student model, you obviously have heads on various tokens. So you have the head on the CLS token, you have a head on the CLS token on the teacher side as well. And then, you also have heads on those patches which were masked. Okay. Now, one obvious thing that you want to do is to essentially ensure that the CLS token from the student model for the view U aligns with the CLS token for the teacher model for the view for the other side view, right? For the other view, right? On the other hand, you also want to ensure vice versa. So essentially, you want to ensure that the view on the student side for the other view matches with the previous view on the teacher side. Okay, the CLS token. So that's the image level objective that is there in DinoV2 as well. Now, what is this patch level latent reconstruction objective? Well, here the idea is that when you basically come up with the reconstruction of the patch here, you want to ensure that this reconstruction matches with the actual reconstruction that you can obtain from the teacher. Okay? So remember, the teacher is basically teacher, so it's obviously better in some ways. And also, the teacher model does not have any masking being done here. So therefore, whatever is the feature or the patch level feature or the patch level representation that you have, that's the one that you want to also obtain on the student side, right? So on the CLS token, you basically apply this objective, right? So essentially, it's cross entropy loss from the CLS token perspective. On the patch level objective, for all those I patches that were masked, you basically want to optimize for this objective where PT is from the teacher side and PS is from the student side, right? Now, the interesting part about DinoV2 and therefore DinoV3 also is that this teacher is not another teacher. In fact, the teacher is an EMA teacher, exponential moving average teacher, which basically means that the teacher weights are actually not trained. I mean, in fact, the student weights are the only ones that are trained while doing this training, right? The teacher weights are basically set as follows. So the current teacher weights are going to be tau times the old teacher weights plus 1 minus tau times the student teacher weights. It's basically exponentially moving averaged over the student weights in that sense. That is how you basically get the teacher weights. Okay, this is popularly called as the EMA teacher, and that's the EMA teacher you basically use for defining both the DinoV2 image level as well as the patch level objectives. Okay. Now, there are more details about this. So essentially, you want to ensure that the CLS token, when this objective is computed, the dino loss, essentially the CLS token for the student is softmax centered. So you take the logits, you basically subtract the center, subtract the mean, and then apply the softmax. So that's the CLS token for the student is softmax centered, but the CLS token coming from the teacher is basically syncon nop centered. So there's a special kind of normalization, syncon nop normalization, which is basically used on the teacher side. Okay. Now, one other loss that you see here is the colio loss. And the Collier loss is basically applied as follows. So you take a batch of images and you take the CLS tokens of those images. You want to ensure, so basically, let's say I is one of those images in the batch, right? So you take the CLS token of image I, right? From the student side. So this is on the student side. And then you find the nearest neighbor of this in the entire batch. So let's say you find the nearest neighbor image in the entire batch. You want to ensure that this entire guy is minimized, which basically means that the distance between individual image features is maximized. So essentially, you want to ensure that the features within a batch spread uniformly in the space. They are basically pretty spread out rather than being very, very similar to each other. Okay. So that's the Collier loss. So essentially, again, this IBOT, this Collier loss are all a part of DinoV2 anyway. So there's nothing new here in DinoV3, yeah, but this is all which is also used in DinoV3, right? DinoV3, however, uses a variant of rope embedding. So rather than using the standard rotary position embedding, they assign coordinates in a normalized -1 to 1 box to each patch. So remember, patches are sort of tiles in the image. So there is two-dimensionality there, right? So essentially, therefore, what you want is a two-dimensional rope representation, right? So the coordinates are assigned in normalized -1 to 1 box. And then these are used to apply a bias in the multi-head attention depending on the relative position of the two patches. So if they're far, they have a certain representation. They're close, different representation, relative representations, right? So to ensure robustness of training to various image resolutions and scales and aspect ratios, they actually apply jittering to this rope coordinates. Okay, so essentially -1 to 1 box is randomly scaled to 2.5 to 2, and that's how basically you get jittering done, and that's the rope variant that they use. Okay. Now, just like DinoV2, they also have 2 global crops and 8 local crops per image. So whenever you take an image, well, basically you can actually get like 10 different samples from the image by having 2 global crops and 8 local crops. Okay. So most of the training, basically all the pre-training, in fact, is actually done using 256 sized images, so 16 cross 16. However, at the end of the pre-training, they also do post-training where they actually, for 10,000 iterations, they essentially use global crops of size 512 and 768 and local crops of different sizes 112, 168, and so on, so as to essentially do resolution scaling, right? And while doing resolution scaling, they also do something called as gram anchoring, which I'm going to talk about on the next slide. So, beside these losses in their pre-training part, also they do something called gram anchoring, which I've not explained so far. So this is just DinoV2. I'll also talk about gram anchoring on the next slide, and which is what they also do in the post-training part. In the post-training part, basically, they also, the model distillation, rather than being done from the teacher, from the EMA teacher, it's actually done using the 7 billion teacher model itself. So, which basically they found to be more stable. Right? Lastly, they actually also do DinoV3. And basically, again, I mean, this model distillation is to distill from the 7 billion teacher model to the smaller models. So for the smaller models, they observed that the EMA teacher does not really give you that good results. So therefore, they basically just said, hey, we will stick to the 7 billion teacher. And that's what we are going to use for distilling to the smaller models, right? Rather than using the EMA teacher. Now, just like CLIP has a multimodal variant, they basically also train from scratch a text encoder so as to support multimodal tasks. Okay, so that's basically the DinoV2 part of DinoV3. Now, further, besides the 3 different losses that you see here, Dino loss, IBOT loss, and D-Collier loss, the Collier divergence loss in that census, they also come up with this gram anchoring loss. And there's a reason why they propose this gram anchoring loss. Okay. So what was observed is that with various kinds of vision foundation models, if you take basically these images and you're basically training them on supervised data, what happens is that all kinds of supervised tasks like image segment, image classification, retrieval, and so on, they keep improving, right? So if you look at this plot, essentially you observe that as you do more and more iterations, with let's say the vision transformer 7 billion parameter model, you see that the accuracy keeps on improving on violation set, right? However, the accuracy for dense patch-based tasks, like for example, segmentation or object detection and those kinds of tasks, there the accuracy keeps decreasing. Okay. So the idea is that if you train more and more on supervised data, that leads to improvements on global benchmarks meaning classification, retrieval, and so on, but degradation on dense tasks, on something that uses global features like image classification and so on, they're going to improve. Image retrieval, they're going to improve, right? But anything that uses local patches, there you see degradation. Okay. So now the interesting part is that they did more analysis to observe that these as more and more training is done, the patches that you basically see, they essentially their representations are not really very sharp. Those representations degrade over time. In fact, here is another visualization to convey that. So here is an image, and after 200K iterations, if you really compute the similarity of this red patch at the center with any other patch in the entire image, you see that the similarity is very high for the petals of the flower, and that makes sense because yellow in color, similarity is high with the petals of the flower, right? And it's a petal as well, petal pixel as well, right? However, as you train more and more, you can observe that the red dot basically has higher similarity to random other pixels, even when using register tokens, by the way, right? So which basically means that this patch level representations are becoming worse and worse over time, although the global representation, CLS token representations are becoming better and better over time. Okay. To be able to not lose the fidelity of these patch level representations, these guys in DinoV3 propose gram anchoring objective. So the object is super simple. So it tries to minimize this thing. What is this thing? Well, it has a student part and the teacher part. So the idea is that on the student part, you essentially take patch level representations, and you compute the similarity between every patch level representation with every other patch level representation. So you basically XS here is a matrix, which is basically number of patches multiplied by the dimension, right? And then so this is called as a gram matrix, and therefore the objective is called gram anchoring. So you have the gram matrix for the student, and you have the gram matrix for the teacher, and you essentially want to ensure that the gram matrix for the student is not worse compared to the gram matrix for the teacher. Now, well, the teacher could be worse as well, so big deal. And therefore, this gram matrix for the teacher is basically taken from an older teacher. So the idea is that as you basically keep training more and more, the teacher also keeps getting worse in terms of their dense local patch dense representations, and therefore what you do is to really take this comparison with an older teacher. So you basically use a gram teacher which is updated every 10K iteration. So you don't really update this gram teacher as frequently as your EMA teacher. Your EMA teacher is actually updated after every iteration in that census, but your gram teacher is updated after every 10K iterations. Okay. Yet another thing is that you don't add gram anchoring objective right from the first iteration. In fact, you basically, these guys basically did all the pre-training with just this loss, this Dino plus ibot plus decollier loss for 1 million iterations. After 1 million iterations, what this propose is that here, after all of that is done, we are basically going to add this gram loss as you can see in the equation at the bottom. Okay. So now what is observed is that, interestingly, if you basically look at this object detection task, object localization object detection task, you observe that so for the first 1 million iterations, while you were not having the gram anchoring objective, the validation loss keeps on decreasing, right? However, as soon as you basically even do 10K iterations, even when you do very few iterations with this gram objective, this suddenly essentially, the accuracy improves. So the accuracy, so this is not loss, this is mean IOU, right? So mean IOU keeps decreasing, but then as soon as you start using the gram anchoring objective, you observe that suddenly there's a jump in terms of the mean IOU accuracy, and it regains back the lost accuracy in that sense. Okay, this is the beauty of the gram anchoring objective. Okay, now obviously gram anchoring objective is basically obtained using this gram matrix. The gram matrix can actually be also computed on a high resolution version of high resolution features, the local patch features, right? So therefore, essentially, if you use high resolution version, you basically get even better accuracy in terms of the dense prediction tasks. Okay, so that's basically the gram anchoring objective. It's basically a regularization method for dense features, and that's basically applied much later in the game after 1 million iterations of pre-training have been done without it, right? Now, how does the DinoV3 model perform? Well, I mean, as you can notice from this picture on the left side, the input image is provided in the first column. Second column onwards, these are basically so PCA representations of patch level features, PCA representations of patch level features, right? So, and each PCA dimension has been mapped to a particular color, and that is how you see these colored images, right? And as you can see, the last one, which is basically the DinoV3 based patch level representations, you can see that they are much sharper, they are much cleaner and more accurate, right? On the other hand, if you really look at the SIGLIP2 or P spatial, perception encoder spatial kind of representations, they are pretty bad, pretty poor in that senses. Okay. Even DinoV2 with regularization is not really awesome, but DinoV3 is much better. Okay, so that basically just tells you the quality of the dense patch level features themselves, right? Now, also, if you look at various dense level tasks like semantics, segmentation, 3D key point matching, or out of domain classification, you basically observe that the DinoV3 family of models is actually much better in terms of accuracy compared to other family of models like DinoV2 or perception encoder or SIGLIP2 and so on. Right. So essentially everywhere that particular thing holds across different model sizes. Right. So and then they have done comparisons across several tasks in the paper. I mean, there are like tens of pages, showing risk tables of this kind. How DinoV3 is really the best amongst all of the other models that are compared across many tasks, like classification, retrieval, segmentation, depth estimation, tracking, 3D correspondence estimation in terms of key point matching, or unsupervised object discovery, video segmentation, tracking, video classification. In fact, even on geospatial data. So they basically, in fact, talk about canopy height estimation. So as you can see these satellite images, one can actually use those images to figure out the height at every pixel, and that's basically the canopy height estimation task. And as you can see, DinoV3 basically gives you much better estimates on this task as well, right? So Earth observation, classification, and segmentation tasks using remote sensing data. So on various tasks, they've shown that DinoV3 really improves significantly and establishes state of the art in many of these tasks. Okay. So they use the VIT 7 billion DinoV3 model. So the 7 billion DinoV3 model is basically also used to train 5 different VIT models and 4 different connext models, right? So as you can observe here, the 7 billion parameter DinoV3 model versus the VIT huge DinoV3 model, they're almost equivalent in terms of performance across various tasks. So these are various tasks, ImageNet task, and then this one is ObjectNet task, which is also classification task. This is basically, and there are other such tasks, right? So there are various other tasks. On many of these tasks, you observe that the accuracy of the 7 billion parameter model versus the VIT H plus model, which is basically 840 million parameters only, the accuracy is almost similar. So the distillation part really works very well. Okay. Now, this table here actually shows for the global tasks and dense tasks, how does the accuracy vary for different model sizes, of these of the DinoV3 model. So S plus is basically DinoV3, a small again DinoV3 model, and then there is a base, and there's a large, and there is a H plus DinoV3 model compared with other other variants of the same sizes. Okay. And you can observe that at each of these sizes, DinoV3 actually gives you better results or comparable results in terms of global tasks, but way better results for dense tasks across different model sizes and across different data sets or different tasks themselves, right? So that's basically how DinoV3 performs. So in short, right, in this video, I talked about DinoV3. It's basically a vision encoder. 7 billion parameters in size, and it has been distilled to various other sizes. So DinoV3 models, variants, vision transform variants, and connext variants are also available, right? Its main pre-training recipe is DinoV2 with the Dino loss, the iPod loss, and the Collier loss in that senses, along with the much larger pre-training data and gram anchoring objective after 1 million iterations plus custom rope variant. Okay. It performs really well on both dense prediction tasks as well as on global image-based classification tasks like classification and retrieval. It basically is a state-of-the-art vision encoder today for various complex vision, computer vision systems like object detection, semantic segmentation, monocular depth estimation, 3D understanding, including camera pose estimation, multi-view estimation, view matching, satellite image analysis, and so on. Okay. So that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.